Okay. All right. Good morning and welcome to the technical forum on radiation health and safety at Jana Elementary. I'm glad to see everyone here today. My name is Renee Dooley. I'm the director for the Center for Environmental Education and Training here at St. Louis University, where we provide training on worker health and safety almost every day of the week. So we're proud to sponsor this event today. No, this just worked, but not advancing. There we go. So I just first want to recognize our host and sponsors, St. Louis University Center for, St. Louis University's College for Public Health and Social Justice are hosting us today. We're very grateful for them allowing us the space to be able to host this technical forum. They recognize the importance of being able to have a place to have some scientific debate and talk about the data. We also want to thank our sponsors, the American Industrial Hygiene Association, the St. Louis chapter, and the Health Physics Society of St. Louis, as well as the Center for Environmental Education and Training. All right, got my clicker working finally. So just a few housekeeping items. If you did not register or sign in on your way in at the table, please be sure you do that at some point today. We just want to be sure we have an accurate capture of who's here. Also, questions. We will be holding questions till the end. We do have a Q&A session that will start at 11:30. I know we hope there's going to be a lot of questions. There are cards distributed on the tables and pens, so as questions arise, please write those down. Around 11:15, we will have a break. I'll have volunteers that are going to go through the room, collect the cards. We'll sort through those the best we can and get to as many as possible. I imagine some of you may have similar questions. We'll also check the Zoom for questions on chat. So if you're on Zoom, please be putting your questions in the chat. And I just want to also remind everyone that we are at a university. There are classes in session. Please be mindful of that. So if you do, take a break, if you're out in the hallway, just be mindful of the noise. We may have students taking exams. It's getting near the end of the semester. And the event will conclude promptly at noon. We do have another class that will be in session using this room pretty quickly after our event, so we do have to vacate this space. So, backwards. Here we go. So, our purpose. Why are we here today? Obviously, we're here to talk about Jana Elementary. I think our purpose is really to review the technical reports on radiation around Jana Elementary. We're going to explore similarities and differences, and by the end, hopefully, we're going to better understand how conclusions were drawn. We rarely have the opportunity to dig deep into science and have experts available, some of whom were intimately involved in the sampling and testing to explain some of the facts behind these reports. So our primary goal with sharing information with one another today is to help improve our bench strength. We've been living with radioactive waste in our community for several decades. It's time to better understand these radiation levels and discuss potential risks to students and others around Jana Elementary. So we hope that today's the beginning of opening up a dialogue between our technical experts, our health departments, and our communities. Only together can we stop the cycle of fear and disconnect over these issues. So we have an expert panel for you today. Murad, can you close that at the top? Yeah, is that, I don't know if that can be moved, but we have an expert panel today. So I'll go through that quickly. First, we have Roger Lewis. He'll be our first presenter. Dr. Roger Lewis is a professor emeritus at St. Louis University School of Public Health and Social Justice, where he has served for 27 years. Dr. Lewis served as division head and later as chair of the Environmental and Occupational Health Department and directed the Environmental Health Research Laboratory located at SLU Medical School for 20 years. And while at SLU, he also managed the St. Louis's Airborne Radiation Detection Station for the U.S. EPA. Next will be Dr. Lee Sobotka. Dr. Lee Sobotka is a professor of both chemistry and physics at Washington University in St. Louis. His expertise spans nuclear and radiochemistry and nuclear physics. He has published about 225 papers in these fields and has studied all forms of radioactivity in his near 40-year career. Dr. Sobotka has received the Glenn T. Seaborg Award for Nuclear Chemistry and from the American Chemical Society and is a fellow of the American Physical Society. He received his Ph.D. from the University of California, Berkeley in 1982 and came to WashU in 1984 and has served on the university's Radiation Safety Committee since that time. And next, Dr. Marco Kaltofen, hopefully I said that right. We had invited him some time ago. We were afraid he wasn't going to be able to show, but last week he surprised us and said, yes, he's going to be able to attend. So we're glad he's able to make it. So Dr. Katolfin is a licensed Massachusetts civil engineer who specializes in environmental investigations involving chemical, petroleum, and nuclear accidents and releases. His research publications are primarily in the field of forensic nuclear science, with a focus on environmental justice issues and nuclear non-proliferation. His studies include industrial accidents and natural disasters, including Hurricane Katrina in New Orleans, the BP oil spill in the Gulf of Mexico, the Fukushima meltdowns in Japan, war-driven petroleum spills in Iraq, and oil-contaminated scientific base in Antarctica, and many more. Following Marco will be the U.S. Army Corps of Engineers. They have a new report to discuss with us today that just came out. So they have a few different speakers that will join us. John Rankins, a senior health physicist. Chuck Finkenbein, health physicist and radiation safety officer with Leidos. Brad Wilson, also a health physicist and radiological lab manager with Leidos. And Randy Hansen, a health physicist and corporate safety officer with Avasi, or Avasi. I may be saying that wrong. And I think we are ready to go. So without further ado, I'm going to switch over to Dr. Roger Lewis.
Hi there. Hope you can all hear me. And I'm going to bring that. Is this your clicker?
Yes, sorry.
Thank you. Well, to start out, first of all, thank you, Renee, for putting this all together. I know it wasn't an easy task for you because you're new here. I've been around for some 27 years, and then I retired a couple of years ago, so it's good to be back. But I know Renee has taken over from my colleague, Chris King, who's sitting in the back here. We appreciate everything you've done, Renee. So we may have a difference of opinion today about various things, but I think we can all agree that for those in attendance, we will be well-fed, well-hydrated, and very highly caffeinated by the end of this morning. So if nothing else, hopefully we can agree to that. So my talk today is called Skepticism and Outrage, Determining Health Risk Inside the Jana School During a Difficult Time. Here are the objectives of my talk today. First, the setting of the talk, environmental justice and outrage. Then I'm going to talk about environmental safety and how health professionals in the communities they serve differ in understanding risk. Then I'm going to talk about uncertainty, a common theme in our profession. How do we best communicate that to the community? Then we're going to talk about the pure and simple truth. It's rarely pure and never simple. And does anyone know who that fellow is in the upper right-hand corner? Oscar Wilde. He was the one that came up with that quote. The pure and simple truth is rarely pure and never simple. How do we find the truth? The way I've taught my students is study the methods. Study the methods. And then
Renee,
and then study the conclusions.
The slides are not advancing.
What's not advancing?
We only see your desktop and the expert panel list. We don't actually see your presentation.
Oh, we're going to stop for a little pause. I have to go get Murad. Yeah.
Sorry, you can continue. I will do my best today.
Okay, well, we're going to try to get our people at home able to see this. I'm going to just continue while this goes on. So as I said, what do? We try to study the methods, and then we study the conclusions, and we develop a consensus opinion based on the entire body of evidence. The setting. Outrage is environmental injustice. The Manhattan Project that left radioactive waste around the St. Louis area is neither a voluntary activity, such as choosing to go to a doctor for an X-ray, or a natural occurrence, such as radon that may enter someone's basement. So we want to go to the next slide. Can I go ahead and just advance this? Okay, thank you. Well, now I'm not able to advance it. Can you advance it for me? Excuse me one moment. So we can't find Murad.
It should be advanced for you.
Okay. Okay. So again, here, the Manhattan Project that left radioactive waste around the St. Louis area is neither a voluntary activity, such as choosing to go to a doctor for an X-ray, or a natural occurrence, such as radon that may enter someone's basement. Radon in homes is the greatest radiation hazard that faces residents in the St. Louis area, but it does not stir outrage. Peter Sandman, a well-known researcher in risk communication, describes involuntary and not natural occurrences as increasing outrage. But I know when Lee comes to talk, he's going to talk about natural occurrences quite a lot. Some major things that create outrage is fear. This is especially so in considering risks to children from things that seem outside our senses and things that we find difficult to understand. Next. What is outrage? What is risk characterization? We need to know both. These are simplified versions of all three equations. According to the EPA's radionuclide carcinogenicity slope factor, excess cancer risk, or risk per picocurie exposure for thorium-230, is about 1 in 28 million. So for every picocurie, excess risk in a population of 1 in 28 million. A picocurie is a very small amount. Okay, we do this to characterize the risk. We need to know the exposure. At best, the lifetime exposure based on expected inhalation over time. Next. Okay, this is one of my favorite slides that was in the New Yorker many years ago, and then it was included in National Research Council book on risk communication. The scientific community is divided. As you can see here, hopefully the folks can see this is a little difficult. Since the scientific community is divided, some say this is safe, while others say it's not. So what is the community supposed to do about that? That's really difficult. When there is uncertainty in a body of knowledge, then Oscar Wilde's quote, "On the pure and simple truth is where the problem begins." So how do we address that? Next. This is how I've taught my students. What are the investigators claiming? Do the results support their claims? And study the methodology to see what it may reveal to answer these questions. This is the approach I take to study the investigations inside the Jana School building. Next. So let's look at my approach to doing this, which many of you in the industrial hygiene community, certainly, and probably the health physics community, operate on all the time. That's sort of your paradigm for doing things. Why was sampling done? What kind of sampling was done? What methods were used? And first, there's lots of different reasons for why sampling is done. To address a perceived risk, to determine ways to control exposure, some combination of both. What kind of sampling was done? Limited screening, or a comprehensive and done with a random sampling design? A combination of both, screening and comprehensive. What methods were used? How was sample determined? What collection and lab analysis was done? How was sampling and analytical error determined and described? Were standard methods used in the study? All of these I look at to try to evaluate a report or an article. Next. So first we're going to look at Boston Chemical's reports. This is the report that was released on October 10th. I'm taking a quote from Dr. Katolfin's report here. Of the 386 microparticles examined in samples from the Coldwater Creek and related areas, 3 out of 4 radioactive microparticles with the highest thorium concentrations came from the Mould Drive Jana School site. Put another way, of the hundreds of samples collected from the North St. Louis County area, none had more thorium than particulate matter found in the Jana School and in nearby homes adjacent to the Jana School. And then below that, there was a picture of Dr. Katolfin's method of using X-ray analysis or scanning electron microscopy to evaluate a dust particle that was 15% thorium by mass. This does not tell us what the average exposure to alpha particles are within the school. What is the toxicology of hot particles, which Boston Chemical references here, compared to diffuse and integrated doses by averaging all exposures over a time period? The ICRP, which is a consensus body on radiation protection, in 1980, determined that no elevated cancer risk exists based on hot particle inhalation as opposed to the same dose over a diffuse area and integrated time period. This has been followed up by more recent literature. In my notes of this PowerPoint, you'll find more recent literature that supports that as well. Moreover, how are these microparticles physically available indoors as an aggregate of dust? How are they inhaled? Resuspension rate. I'm an aerosol scientist by training. That's most of my background. Most of my laboratory work was on resuspension of aerosols. Resuspension rate depends on surface loading and depth of particles in surfaces. First of all, you have to have mass. You have to have mass to have risk. You have to have a certain mass of particulate somewhere for inhalation to exist, not 1 or 2 particles, a mass. Resuspension rate depends on surface loading and depth of particles in surfaces. How much surface dust was present where Boston Chemical sampled? I think you probably used like a tape lift or something, I think Boston Chemical, as opposed to a filter where you actually wiped a surface. Tape filter does not tell us about exposure. What it does tell us is something that's present. So Waldo, for instance, where is Waldo? Boston Chemical's approach to this microparticles is a little bit like, where is Waldo? Where is a hot particle? Not the exposure that Waldo has, but was he there? But that doesn't inform risk according to the body of literature that we are familiar with as scientists. Next slide. Going. Okay, we'll stop there. Here's another part of Boston Chemical's report that I have a lot of questions about. And that is the following. This is a quote from the first report. Likewise, lead-210 and polonium-210 were found in indoor dust in the Jana School kitchen at a combined total activity of 27.8 plus or minus 3 picocuries per gram. What does this combined activity mean, and over what area was this sampled? Is this a sum or an average? Is Boston Chemical counting alpha particle emissions twice when only the polonium-210 is an alpha emitter? This calculation is an error. It doubles the actual activity found with no evidence to support the claim. To determine the risk, we need to know not only the radioactive concentration, but the dust loading as well. And we don't know that here. How much dust was available for ingestion or inhalation with particles about 1 micron in diameter for inhalation? We don't know that from this. We can't determine risk without knowing the area sampled and the mass of dust on the wipe. The denominator will inform what the concentration is in activity per area sampled. So let's look at the methods themselves that were used, and we'll do this for each of all the groups. Was sampling done to address perceived risk? Yes, that's what Boston Chemical did. What kind of sampling was done? Limited screening. Well, they didn't have a lot of time. It was limited screening. A lot of people do that. I've done tons of investigations like that. What methods were used? How was sample size determined? Not given. We have no idea how the sample size was determined. Were collection and lab analysis methods clear? Mostly. How was sampling and analytical error determined and described? Well, it wasn't given for the SEM X-ray analysis for the hot particles. However, I know from his previous papers, which I've read, that he goes into great detail on those methods. So I know it's out there, but it wasn't in this report. Were standard methods used in this study? Unclear. Here's another quote. This is based upon the supplemental report that BC turned in to, well, Lee Sobotka got a copy of it, and then I got a copy of it. Boston Chemical asserts that the SCI company that did an independent investigation underestimated risk by including negative sample measurements in their mean radioactivity of reports. However, one thing to note is that that is best practice to include all your results. If you have many more samples and many more background samples, they just took one background sample. SEI, if they'd taken many more, over time, you would find that the results would be positive. So according to best practice, you report all these values, even negative values, because if you don't, then you're going to overestimate risk. We don't want to underestimate or overestimate. We want to include all the data, and that's in conformance with best practices. That includes the National Council on Radiation Protection and Measurements in their Handbook of Radioactivity Measurements, also a report by Brookhaven National Laboratory, and answers to experts in the Health Physics Society. SEI's indoor dust sampling. Now we'll pick on SEI. We're not going to pick on BC anymore. Okay. Why was sampling done? To address a perceived risk. What kind of sampling was done? Again, limited. They didn't have much time. How was sample size determined? It wasn't given. Okay, were methods clear? Mostly. Was sampling and analytical error determined and described? Yes. Were standard methods used? Yes. Was given. Here were their summary results. You can see the analyte, uranium-238, thorium-230, and lead-210. Their averages are all below background. Again, they have a negative background. If they had done lots more sampling, if they had more time, it'd probably be a positive background here, and they wouldn't have negative results in their data set. Well, let's go to the Army Corps of Engineers. Why was sampling done? To address perceived risk? Yes. What kind of sampling was done? It was comprehensive and done with a random sampling design, and a combination of both screening and comprehensive was done. So they had both a biased kind of sampling where they used professional judgment, and they had a random sampling design where they used the Marsa manual, which is a well-recognized manual of how to do radioactive investigations in Superfund sites. So that was how they determined sample size. They used the Marsden manual. Were collection and lab analysis methods clear? Yes. Was sampling and analytical error determined? Yes. Were standard methods used? Yes. This is their preliminary report. 19 measurements. And by the way, I'm just talking about the indoor environment here. They're going to be talking about structures today, so I'm just talking about indoor air samples. Their mean was 0.95. This is picocuries per gram. And their maximum was a negative 0.23. So negative results mean that the analyte was not present or at levels below laboratory systems background. The greatest minimal detectable activity was 1.96 picocuries over 100 centimeters squared. So they give us an area. That's what you need, guys and gals. You have to describe your exposure in terms of a denominator that has area. Otherwise, we really don't know how to figure out risk without knowing that denominator. Finally, the Army Corps final report on indoor swipes from 5 locations. There was insufficient dust available for lead-210 and polonium-210 analyses. The radium-226, 228, and thorium-230 were at concentrations near minimum detection. Risk characterization and dosimetry scenarios for inhalation and ingestion result in risk and dose well below health-based remediation goals for children in schools, staff, and residents of area. They came out with their final report sometime late yesterday. I was able to look at it. I didn't read all 400 pages, but I'm working on it. But that's what I found. And I looked at the data as well. I combed through a lot of different things. I looked through their model building as well, which I know we have a gentleman here to talk about that. Conclusions. Do the Boston Chemical investigators present sufficient evidence to support the hypothesis that there are harmful exposures to radioactive materials inside the Jana Elementary School? No. Okay, no. They didn't prove their case. Why? Because the methods weren't standard. They didn't use standard methods, and the methods that they did use weren't supported by well-known consensus experts on radiation, as well as industrial hygiene in terms of exposure assessment, in my view. What is the consensus, though? That there's no harmful indoor dust that poses radiological exposures at the Jana Elementary School from when it was investigated to now. Okay, and these are the folks that would agree with that. The Army Corps of Engineers, SEI engineers, peer reviewers, myself, and no surprise, probably Lee Sobotka, but I don't want to ruin your entrance. Maybe you've got some surprises for us. Okay, what needs to be done? Clean up, abandon and rebuild, or nothing? Well, like I said, from the inside, from the interior, there are no harmful levels of radioactive materials. Radon, that was checked out by the health department some time ago, and you're good with that. But if you decide to do more, you can clean up more. I mean, if you want to clean up, you find something to clean up, I guess you could. But I guess my point is, if we have something like asbestos or mold or lead in pipes, do we abandon our school buildings? No, we remediate them. They're too expensive. So if we find something in a building, we just clean it up. In this case, we don't have anything harmful. But if we do, if someone like Dr. Katolfin thinks that there are, we could always clean up. But to the extent that it's really necessary, I don't think so. Thank you.
Okay, my name's Lee Sobotka. I'm not a health physicist, but I do know a lot about radioactivity. And I'm going to tell you provide some context for the discussion. about Jana. And I want to stress we're talking about Jana, not the greater problem in St. Louis, because every place needs its own discussion, every local environment probably. Okay, so what am I going to do? I'm going to go through some units that we have to understand. I'm going to talk about natural exposure a little bit and its variation. I'm going to go at various points in this talk, there's going to be a set of questions. And there's questions that are kind of, you can ask them, but they're really missing the point. There are better versions of those questions. There are intellectually maybe ivory tower questions that are really, boy, I'd really like to know the answer to that. And it may have an impact on what you do, maybe not. But then they're the ones that really matter, okay? And one should, these category, there's no firm walls on these, but should know where they are, these questions are in that scale. I have to introduce you to my second favorite organizing chart. The first one is the periodic table, but the next one is the chart of the nuclides, and I'll introduce alpha, beta, and gamma radiation. I'm not sure everyone in the audience is super familiar with that, and also quality factors and linear energy transfer, which become important. I'll talk about natural decay chains and secular equilibrium and how humans can break it. That's important because I think we have a question that needs to be answered, and I think it is answered in the data, and people have to appreciate that. I want to go through a little bit of the history of the how we relocated natural material from Belgian Congo, natural but really unusual, locally, and what Mallinckrodt did. I'll actually have a complete flow chart of the chemistry. I will just show it. You can look at it later, but it's important for the question of breaking secular equilibrium. And then what happened to what Mallinckrodt really did. People often talk about it, well, it was for making bombs. What really they did was purify the uranium, and most of it went to reactors. Tiny, tiny fraction of it was sent to be enriched, but that was not really the goal. The goal was to make the uranium for reactors. And all the early reactors ran on stuff that came from Mallinckrodt. Now, I do want to talk about how humans influence background radiation. You say, well, wait a minute, background radiation, what does it have to do with humans influencing it? Well, we influence it a lot, and I want to go through how humans influence background. Okay, since Marco is here, I'm not going to actually talk about his results. In fact, except one thing where Marco was very nice to send me something, and so I'll show a spectrum from Marco's work, but most of the time I'll talk about SCI results. They're not here. So I said, well, why not just use I don't want to use the Army Corps. They're going to present their own results. So I'm going to mostly use SCI. And then I'm going to bring to light a study from Baltimore. And you may say, well, why does a study from Baltimore have anything to do with what's happening in St. Louis? And you'll see why it's very relevant. And then some conclusions. So let's see, which one of these things is, okay. So here's a map. You see the map. Everyone knows a map. Move on. Okay. So, some of the units and distinctions. So we talk a lot about decay rates. That's radioactive decay is the simplest differential equation to solve. It's a first order a differential equation, and it leads to, I'll actually show some equations in a minute, but the decay rate named after Madame Curie is the Curie, and it's a huge rate. If you're in a room with a Curie, you better run like hell, okay? And that's 3.7 times 10 to the 10th decays per second. It's a round off of how much radioactivity there is in a gram of radium. It's a historic unit that was rounded and fixed. And so that's that. We talk about a picocurie. Now, a pico is 10 to the minus 12. Okay, that takes a big number and makes it a tiny number. Okay, so that's how many decays per second in a picocurie. Now these units are used really in the United States and not much else in the world. They use an SI unit. The SI unit is the becquerel, and that's 1 decay per second. Nice, easy to remember. And you'll need this conversion from picocuries to becquerels a little later. So if we have a certain number of becquerels, see this is a smaller number here. So you have to multiply becquerels by about 27, call it 30, okay? So if you have a number of becquerels multiplied by 30, you get picocuries, okay? You'll need that number later. Now, we're not really interested in this. We're interested in the effect of that radiation on humans. So there's an intermediate step, which is how much radiation is absorbed in a gram of tissue, okay? And that's the older unit is called the rad, and it's a CGS unit, 100 ergs per gram, and gray is the SI unit. But why, you say, what's the logic here? Why would you care about not the total energy deposited, but the energy deposited per gram of material? And that is, we evolved on this planet. It's actually a rather wicked planet. And we would not survive if we didn't have proteins that ran up and down on DNA repairing single-strand breaks. We live because we have repair mechanisms for radioactive decay. And we have it everywhere in our body. It's working right now in all of you, okay? And so you want to know how much the damage is per unit of material because so many grams of your tissue have so many of these repair mechanisms functioning. So you don't want the total amount of decays per second. You want, or energy deposited, you want the energy deposited per amount of material. But that's not quite right either. And the reason is different radioactivities can leave different amounts of correlated local ionization. So there's a difference between single-strand DNA breaks and double-strand DNA breaks. I won't go there, but alphas are particularly bad because they leave correlated damage and can create multiple damages on the same DNA within a strand within a certain region called double-strand DNA and cause double-strand DNA breaks. So there's a quality factor that makes that correction. And that I can't give you an exact number for alphas because it depends on their energy, but so you have to take a decay rate, make these conversions, make this correction for the quality factor to get the so-called REM, the amount of, which is Rankine equivalent man, that's the dose you really care about. So we might focus on this, but we really care about this. Okay, right button. So we really care about this, not the origin of the radiation, okay? We really care about what the total potential damage is, not on where it comes from. All right, now natural exposure. We live on this planet. We're bathed in cosmic rays. You're being bombarded with them right now, and your body's responding to them. If you go up in altitude, you get more of them. In fact, one of the limitations on how much time a pilot can fly is the number of hours due to the radiation dose that they receive flying. Now, there's many limitations on the number of hours, but that's one of them. All right, here's a plot of this first part as a function of altitude. This band here is where a plane flies. This is proportional to the exposure rate, so it's like here at 10. This particular detector would be 10 counts per minute, and it's about 125. It's gone up over an order of magnitude by flying at that altitude. Okay, but in addition to that, the natural part, the major part of it is these natural decay chains I'll talk about in a minute. There's some parts that are internal to you. Potassium-40 will come up later. Carbon-14 is present due to if you're alive, you're exchanging with something that's created the atmosphere. And so you add up to some number, depends on altitude, but say 150, 200. And this is in this appropriate units, millirems, and it's per year. And then fallout, add some more, but mostly the addition comes from the medical exams that you might have, x-rays and so forth. Okay. Okay, so questions from marginal to good. Is any particular sampling near background? Okay, it's a thing you can ask, and it's kind of good to keep in your back pocket. A bigger question is a set of samples near background? An interesting question is an activity above normal background? Let's say you find something that's above your nominal background. I'll say green field background. In this case, is it due to Mallinckrodt raffinate, a term I'll describe in a minute, infiltration? That's what people are talking about, that this waste from Mallinckrodt got somewhere where you didn't expect it to be. Or is it due to some other process, and I'll call it concentrated natural or anthropomorphic human-generated concentration, okay? That's not this one. So I'll make a distinction between A and B, and I'll have a figure that distinguishes them. And the question is, can you create a signature that differentiates A from B? And I think that's an interesting question, but this is really the best question. In the end, really what you care about is, does the dose, regardless of origin, pose a risk? So this is the academic. That's really where you want to be. Okay, here's the chart. Periodic table, it would be splayed up this way, different isotopes this way. This is very light end. The chart of the nuclides will actually deal with an isotope way down here in a minute, you'll see. The actinides are up here. So here's uranium-238. It alpha decays to thorium-234. That's take away 2 protons, take away 2 neutrons that are in the alpha particle nucleus. So that gets you from here to here, and it's a diagonal. And the 3 natural decay chains, which I'll talk about in a minute, are those 3 stars up here. They're on the Earth for one and only one reason. Their half-lives are commensurate with the age of the Earth. So the Earth was born with them, and we are going to live with them and until way past human existence on this planet. They'll be here. Okay, on this side we have beta decay, and this beta minus. On this side we have beta plus. Here, and then if you have an excited state, you'll go from an excited state to a lower lying state by the emission of gamma. This quality factor is 1 for gammas, usually about 1 for these electrons, and higher for the alpha, variable with energy. Okay, these are the 3 natural decay chains, starting with uranium-238, a very easy number to remember if you know the age of the Earth, which is 4.5 billion years. And it just turns out that the half-life of uranium-238 is almost identical, so get 2 for the price of 1. Thorium-232 has a very nice, easy to remember lifetime. It's actually the age, not of the Earth, but of the universe. Now, if you don't know that number, that's 14 billion years. You get, again, 2 for the price of 1. Happens to be coincidence. I'm rounding. Okay, and then uranium-235, which is much shorter, which means if you go back in time, the uranium-235 grows faster than the uranium-238. So if you go back in time, you get enrichment. Okay? Very important fact for another subject, another talk. Anyway, so you start up here with uranium-238, alpha, beta, beta, alpha, 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 beta, beta, alpha, beta, beta, alpha. And I want to focus on this part down here, which is important. And by the way, all these chains end in some isotope of lead. The uranium-238 ends in 206, in lead-206, which is blown up down here. We're going to talk about lead-210, and it has a 22-year half-life, beta, beta, alpha decay to lead-206. Therefore, if you're concerned about REM, or Roentgen equivalent man, you're interested in this alpha decay. And there is one alpha decay between lead-210 and stability, lead-206. You should multiply by 2 or any other number. If you are talking about the total number of picocuries, yes, you would multiply actually by 3, but these two contribute almost nothing to REM. And so if you want a number that's related to the actual damage, whether you talk about the decay rate of lead-210 or the decay rate of polonium-210, it's the same number. And if you look at the Eberlein studies, they are identical, okay, because there is really only one measurement of this process. Okay, so that's important to keep in mind. Okay, so secular equilibrium. So this is a little, so that's the differential equation, as I said, the simplest one could ever imagine. And think of it this way. You have a bucket, and that bucket has a tiny little hole. A tiny, 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 tiny hole. Oh, maybe I forgot a few tinies, okay? So really tiny hole, and it's dripping out, and these buckets below them have much larger holes. So put that in your head. And you ask the question, what is the rate of water emptying out of this bucket, or emptying out of this bucket, or emptying out of this bucket? And you see they're all the same, because the upper bucket is just dripping out, and the other, that's how much I have left? Okay, so, okay, so the rate, so they're all saying the same rate, okay, because the upper bucket has such a small hole. That's called secular equilibrium. That's what you expect from a natural undisturbed sample, okay? And so the decay rate of each is equal to the parent, equal to the first daughter, second daughter, third daughter, all the way to the end. And if I went back one, that's all of these would have the same decay rate if you had secular equilibrium. But humans can screw that up. All right? So, and a colleague of mine wrote a little article about, well, maybe, oh, let's go back. Let's say we take this bucket and we take it out for a minute. We empty it. Okay, and then we put it back. And we ask, what's the decay rate? Well, this bucket hasn't gotten anything in it. It's empty. So in fact, all of this is zero if you've taken that bucket out. And you can do that with chemistry. And then this one hasn't been changed, but it will take a while to reestablish secular equilibrium. In fact, in time, the radiation can grow. Most people think the radiation must always decrease in time. Not so. If you have secular equilibrium, this radiation rate has not changed, but these have been taken out because you removed this bucket and it's empty, then you put it back, and all of these will be at zero, and then they'll grow in. How long does that take? Well, it can take a long time depending on the half-lives of all of these things. So the question is, are we in a realm where the radiation could actually increase? It has to be answered, that question. Okay, wrong button. Whoops, wrong way. Okay. What Mallinckrodt did, I give it here, you can look at it. It's a wartime effort. Actually, it's kind of a heroic effort, if you ask me. And mistakes were made in any real process, and a lot of mistakes were made afterwards. But I think what was accomplished by Mallinckrodt shouldn't be dissed too much. It was really an amazing thing they did. Okay, so green field. What did we do? We went to Africa, where the natural radioactivity was not a few picocuries per gram, but over 1 million picocuries per gram. That was natural, not man-made, okay? But we dug it up and we moved it to a green field, St. Louis, okay? And we did chemical processing. So keep in mind that natural does not mean low background, that natural does not necessarily mean safe. That's not safe, okay? That's the chemical processing that they did. We're worried about what's called the raffinate, which is a separated part of the extraction process, which contains the daughters. Where was the uranium used? Fermi's reactor. That's a painting. It's an interesting story on why they don't have a picture. A reactor in Oak Ridge and a reactor in Hanford B. That's where the uranium went, almost all of it. Okay. All right. So I talked about taking natural, moving it somewhere else, a very unusual natural, polluting the environment. Is there any other ways that humans, so this is a human chain, humans caused this relocation of material and caused this very unusual situation. Is there anything else we do? That's sort of intentional, but is there anything else we do? Yes, actually there is. So if we take a green field and we build a parking lot, do we change the background? Yeah, we do. And I'll describe why. Whoops, wrong button again. So let's go. This is the SCI results. And for a bunch of isotopes, so first to this question of secular equilibrium. And one way to evaluate it is to look at the ratio of thorium to radium, basically two buckets. If they're in secular equilibrium, that ratio should be 1. If it's been disturbed, it might not be 1. What's the average of all of these? 30 measurements, 0.92, standard deviation of 0.6, consistent with 1. There is a high number of 4, but you'd expect that, occasionally you're going to get that. Many numbers right around 0.4. There's no reason to see, there's no indication here that secular equilibrium has been broken. Therefore, it is consistent with a natural green field situation, okay? Now, I'm not saying that's what it is, but we don't see this possibility. In Jana, I don't see an opportunity for the radiation, whatever it's caused by, to increase. And it could be that if it was infiltrated by Mallinckrodt waste, but I don't see it. Okay, one sample though, here has high lead-210, 42 picocuries per gram. Okay, and I want to return to this, or I'm going to get to it just in a minute, this number. Oh, by the way, I have to go back. That's where it's taken. Okay, that's where this high number was taken. Sampling was taken. And obviously that's not greenfield. Humans created this thing, this parking lot. Dust, radon testing, other things from the SCI, nothing stands out as being a problem. Now this is this sample 28 S8, right in this location. I showed you that dirt spot on the asphalt there. There's another location which we might get to. Now, the study from Baltimore that you might think was irrelevant. Okay, so there's no Mallinckrodt waste here. But what they were interested in is, could they tag the downstream effluents from rain where they came from? Okay, some of their initial motivation is irrelevant. But this is what they found. They found a concentration from what I'll call fallout. And so down here, these squares are sort of, if you will, mean water. And these triangles here, which are way down, not too much different here for cesium, but highly elevated for lead-210 and beryllium-7. They're highly elevated on pavement places which aren't draining well. Okay? Why? Let me explain what's happening here. Cesium-137 is not natural in our atmosphere. It's only there because humans put it there. Before 1963, we were blowing off, us and the Soviet Union were exploding bombs in the atmosphere. The Limited Test Ban Treaty, I think the most significant thing that Kennedy did as president, was signed, and atmospheric tests were stopped. Since then, and there was then subsequently some nuclear accidents also put cesium in the atmosphere, but it comes out pretty quickly. By the way, we're celebrating the second half-life anniversary of the test ban treaty. We've got, okay. So it's high for lead and so that's not in our atmosphere, the cesium. But lead-210 is continually, because in those natural decay chains you have radon-222. It'll rain out, but radon is made continually from those chains. It's put back into the atmosphere, it'll come out. Put back in, comes out. It's always there. It'll always come back out. Beryllium-7 is a product of cosmic rays in our atmosphere. It will come out it has a short half-life, by the way, something for 44 days, but it's constantly being made, constantly being rained out. And so those two things are natural in that sense. And they are much in excess, found much in excess in these kind of locations, man-made repositories due to poor drainage by significant amounts. Now, I asked you at the very beginning to remember this number 27. Okay, that's the number to take to go from these units, which are becquerels per gram, to picocuries. So if you take 1.5 and you multiply by 30, you get 40. So it's basically those high numbers we were seeing before. But wait a minute, there's something more here. There's a fingerprint. If you see high lead-210, maybe you should look for beryllium-7. Beryllium-7 has nothing to do with Mallinckrodt waste. Zero. Okay? So, quickly, Marco sent me one of his spectra. Okay? And so this is the sample that had the high lead-210. 42, 43, something like that, picocuries per gram. You can't see this, so I'm going to blow it up. I'm going to blow up just the low point down, the low part down here. So what's conspicuous in this gamma ray spectrum that has the high lead-210? By the way, the lead-210 is down here mixed in with two thorium peaks. But let's start from the top. This conspicuous peak here is potassium-40. It's in all potassium. You have it all every day. And if you have someone that can't take sodium and they get no salt, they're loading up on this. Okay? Doctors tell you that you have to get your sodium out. You go take sodium, we'll take no salt. They're telling you to eat this. Okay? So that's one of the peaks. It's way out there. The efficiency of the detector is actually dropping, so it's larger than it actually looks. Notice this peak down here, the cesium. Cesium is small. Remember, cesium was the thing that this Baltimore study said was not enhanced in these locations. And there it is, a little puny peak. Well, what did they say was enhanced along with the lead-210? Beryllium stuff. Nothing to do with Mallinckrodt waste. This was the hot lead-210, and it's co-signaled or co-present with beryllium-7, which comes down with the rain. Okay? Which button? This button? Okay, so now conclusions. I think I'm about right. He was telling me to rush. Sorry. Okay, so what do I got? The ratio here of thorium to thorium-230 to 226. I'm trying to figure out whether we have this secular equilibrium breaking and the possibility that the radiation could increase in time because the buckets were empty below and now they're filling up, and over time they'd fill up and they'd start raining down too. If this number was greater than 1, that means an upper bucket was filled and the lower bucket was empty. If it's equal to 1, that means you're in secular equilibrium. It's just looks like natural. And we looked at Jana, and the answer was yes, it looks natural. We don't have this problem at Jana. I'm not saying it doesn't happen elsewhere. I'm saying at Jana doesn't look at it. In the aggregate, the samples, wipes, air monitors are not a cause for concern. Now, the high lead-210 is interesting. So this is the academic question. It seems to be localized and could result from concentration of natural or fallout material from man-made impervious surfaces where water flows, but it doesn't all go, everything in the water doesn't go down the drain, okay? It collects. So the rain comes down and it collects, okay? It'd be nice if, for this subject, if it didn't rain for half a year. If it didn't rain for half a year, just follow me here, the beryllium-7 will go away on the ground because it's a 44-day half-life. I don't really want that to happen. Farmers would kill me and we would be, you know, but just realize that it's always coming down and okay, so so it's consistent with that, this high lead-210 sample, but realize it's not the lead-210 beta decay that you care about, or it's gamma decay. You care about the alpha decay from the polonium-210. All right, to address this academic issue, when someone finds a high lead-210, an elevated 210 that's making them scratch their head, is this a problem or not? One should look for beryllium-7. One should just look at the gamma ray spectrum, see if that other peak pops up. If it does pop up, it's more likely natural, or this human-made natural redistribution from just things like making parking lots, rather than infiltration from, say, Mallinckrodt, more likely. If you don't, and by the way, then you also shouldn't find cesium. So it's a fingerprint, 2 things up, 1 down. Okay, if you don't see that, then you can go to the next step about thinking about infiltration of, say, raffinate. But still, and that's an interesting question, and people should do it. So I would encourage, whether it's the Army Corps or Marco or SCI, when they see a lead-210 that's elevated, go look at the spectrum. See if beryllium-7 is there. Okay, I think it's a marker. All right, that's an interesting question, but it's not really the important question. The important question, is there an evidence for elevated dose, REM, and thus risk at Jana? And I didn't spend a lot of time talking about this, but I don't see it. Does this mean that the school property should be redeployed as a school? Well, I don't, so I'll separate this part in 2 things. Radiologically, I don't see why not. Yes, maybe some cleanup, as Roger was saying, but I don't know that that's really the issue anymore. The question is, will the public find confidence with that outcome? And if they can't have confidence with it, then the consequences of that may make the school untenable. But that's just where I'm standing. Perhaps things will evolve and people will find comfort on this. But I don't think there's a radiological issue not to redeploy as a school. That's it. Thanks.
Thank you very much for having me here. Renee, can you put that full screen? Thank you. And I also want to thank Dr. Lewis and Dr. Sobotka for having me here today. Believe it or not, I actually agree with about 95% of what they said this morning. And in particular, I agree with Dr. Lewis's introduction, where we talked about the idea of doing comprehensive testing, comprehensive risk assessment. It's important to know that there are 14 different public school properties that are along Coldwater Creek that we understand as having, that is, the creek is contaminated with material from the Mallinckrodt works. And right now there's a bill that's before the United States Senate that's being sponsored by the senator from Missouri, Mr. Hawley, and the congresswoman from Missouri, Ms. Bush, and has been endorsed by the Honorable Jennifer Granholm, who's the Secretary of the Department of Energy, and Dr. Lewis, that comprehensive testing is the way to go, not just with Jana, but with all these properties. And I very much agree. Can we do the next slide? So I'm an independent scientist. I've done work academically in the area, and I've also done work on behalf of a law firm that is suing the Mallinckrodt Corporation, or I should say, I'm going to let the lawyers explain that sometime. But I'm working for the law firms, and I've been working independently. I don't work for a government agency. But we've had the opportunity to look at a fairly large number of samples from this area and see some of the different kinds of materials that are present, and actually follow the waste from Mallinckrodt and how it was transported to different locations, and very importantly, the physical form and how that is transferred. And it is a complex story. And again, this is why I think comprehensive testing of public school properties actually makes sense. We're analyzing for a fairly large number of different isotopes. We're using multiple methods. These are standard methods of analysis that are approved by the US EPA or the NRC. And the laboratories that we use to do our work are the same ones that are used by government agencies like the Department of Energy, the US Army Corps of Engineers, Jet Propulsion Lab, NASA, NSA, Department of Defense, so that the methodologies that we use are comparable. And in fact, the data that we have acquired in general is comparable. But there are definitely some differences in interpretation, and also some differences in how we understand what that means. Can we do the next slide? For example, one of the things that we've done that hasn't been done as commonly is to look at the individual soil and dust particles that actually carry the radioactive material. So radiation is not so ephemeral or phantom-like as we might think, even though we don't see it. Radiation is normally carried by particulate matter, soil and dust particles, everyday objects. And they actually contain the different elements that were in Dr. Sobotka's chart, the chart of nuclides, that actually deliver the radioactive dose. And not to be too agreeable today, but I very much agree with what Lee had to say, that it's not so much the picocuries, it's the dose they exert. It's the energy that is delivered to a cell that really matters. Because it's that energy that actually is causing the biological damage that we're talking about here. And what we find when we look at the dose that's delivered, it turns out that dust particles, dirt particles, especially small microscopic ones, are efficient ways to deliver radioactive energy internally. So not externally, meaning if I walk by a radioactive object, what did you say, run? If it's a very high number, like a curie, agreed. This is an important safety tip if you're seeing that kind of radiation level. What we're talking about here at Jana School is a little bit different. We're talking about a dust particle that can be inhaled or ingested and then becomes a permanent souvenir. It's in your body. And it is exerting that radioactive dose. It's delivering that energy continuously, whether or not you run. So that's obviously the worst case. This is the kind of thing that we want to avoid when we're talking about radiation exposure. And I think we all agree that radiation exposure, even small radiation exposures, are not good. The US EPA says that there's no safe level of radioactive exposure because ionizing radiation, even small levels, can potentially cause harm. So the safe level is obviously 0. We can't do that in this world because, as has been said this morning, there are radioactive objects around us, perfectly natural. The fact that they're natural doesn't make them safe. Arsenic is natural, it's not particularly safe. And our question is there material that is particular to the Mallinckrodt waste that's in Coldwater Creek that's getting into the schools? So one way to ask that is to look at that dust and soil material and actually see whether the dust particles, the soil particles, have the same elements that are in the Mallinckrodt waste. So let's think about this test. One of the things that I did in my work is I used a laboratory that looked microscopically at individual particles that contained thorium, which is really the most important indicator element for radioactivity related to Mallinckrodt. Not so much uranium, because uranium was what they sold. They got money for not putting uranium in Coldwater Creek. So surprise, surprise, there's not a lot of uranium in Coldwater Creek compared to thorium. If we look at the actual percentage of different materials that are in these particles, copper, cobalt, vanadium, different rare earth elements, it turns out that the particles we find in Coldwater Creek and within the Jana School and in other areas like that pavement sediment that you gave us a photo of, the elemental makeup of those particles that contain thorium matched the elemental makeup that Mallinckrodt said was in their original material. Could we go to the next slide? So this is from 1955. These are the elements that Mallinckrodt said are in their thoriated waste, their waste materials that contain thorium. And so these rare earth materials, for the most part, well, plus copper, vanadium, cobalt, the things that that they attempted to recycle from the Mallinckrodt waste, are the things that are diagnostic of that thoriated material from Mallinckrodt. And it turns out that when we go back and we look at what's in those thorium-containing particles that we collected from the Jana School and from other places all around the area, match up to what Mallinckrodt said we should expect. Can we go to the next slide? The other kinds of analyses we talked about are the gross analyses, meaning analyses of a handful of soil or where it was available dust. And yes, I definitely get this practical problem of there's often not enough dust to test. And this is why cleaning is actually important for reducing exposure, but that's another story. When we look at the total amount of radioactive materials that are in the different samples we take from the Jana School, these actually line up fairly well. And in fact, in important ways, for the thorium-230, which is again, the diagnostic element for the Mallinckrodt waste, the Army Corps' numbers are actually a good deal higher than mine. In fact, the maximum number that the Army Corps found in their results closer to the school, further away from the creek, in the shallow subsurface, were 9.65 picocuries per gram. This is much higher than my maximum result. It was 0.94. So 10 times higher than what I found. And again, they took more samples. And again, this is why I agree with the representatives in Congress who want the Army Corps to look at all of the schools that are on Coldwater Creek. So we don't argue a lot about the magnitude of these different numbers. Where we argue is this important to our children's health? What's actually happening? Next slide, please. We have background numbers. Just to be clear, the Army Corps, the US EPA gives us different background numbers. And there are multiple samples that exceed these backgrounds from close to the Jana School and certainly from the creek nearby. But again, our discussion is focusing on, how does this matter for the children and staff at the Jana School? Next slide, please. This is how it matters. This is a photograph of one of the particles taken from the Jana School. This is taken from that kindergarten location where we have the photograph showing the pavement sediment. It's outside the kindergarten play area at Jana. And this particular particle right here, it's about 6 microns across. It's a little big to inhale, but certainly small enough to ingest. Does anybody notice, by the way, that little kids are good at ingesting dirt and getting dirty? This kind of a truism. We understand that children do a lot of hand to mouth. We do it. COVID taught us that we do this. And children do it in fairly large numbers with great regularity that we know from EPA models that these children will get a dose from the dirt and dust that they come in contact with. I mean, we call them rugrats for a reason. Small children spend their time down there. My wife is a public kindergarten teacher. Kids spend their time on the carpet, hands and knees, all fours, sitting in a circle for story time, whatever. So that hand-to-mouth activity is an important way we take picocuries and we convert that to dose, energy actually delivered to cells. And this is the mechanism where it happens. We look at those individual particles. Now, there's actually a natural amount of these materials in the environment too. We often find thorium in thorium minerals, maybe as much as 3 or 4%. But 15, 16, 17%, this is actually quite rare. And in fact, from samples taken in the area of the Jana School, actually from a home that is adjacent to the Jana School, we found a particle of 70% thorium. At 70% thorium, this is a manufactured object. This kind of material cannot exist in the environment naturally, except in rare extremes. It would be very unusual for our group to be able to find such a thing. So that tells us that these thoriated particles, which have the same composition as what's from Mallinckrodt, which are located in a floodplain of a creek where we know there's literally tons of this material. And we're finding similar materials in the homes around the Jana School, are actually important and related to the waste as opposed to fallout. And this is important because when we think about, I keep coming back to the area with high lead-210. The kindergarten play area is also the area where we find the maximum level of radium-226, bless you, which is not related to radon, which is not related to airborne fallout, which doesn't move in sync with beryllium-7. And yes, the beryllium-7 issue is very real, which is why when we quantify the lead-210, we actually chemically separate the lead-210 from the beryllium-7 and other isotopes before it's measured. So that original gamma spectrum is not where we get that number. We actually chemically separate that out and do it separately. But lead-210 is just one of the issues. And it's why this, and this was Dr. Lewis's introduction, the idea of looking at the entirety of evidence, the preponderance of evidence. We go to the kindergarten playground and we see, yeah, there's pavement sediment with lead-210. We did chemically separate. We also know that that's the maximum impact spot for radium-226 in the surface. And we also found that of all the samples that we collected, it was the most prolific in terms of having a large number of these thoriated microparticles, which we can see in photograph. Next slide, please. So the homes where we found the very high levels of thorium in radioactive microparticles here along Moole Drive. If you're not familiar, there's a tributary to Coldwater Creek, which also floods. And that tributary backs up and floods people's basements. And the Agency for Toxic Substances Disease Registry tells us in their written report about Coldwater Creek just 3 years ago, that when those floodwaters recede, they leave behind the radioactive material in Coldwater Creek, actually inside the home and in the basement. And that's what our analysis confirms, that this material is left behind. It is related to Mallinckrodt. And it is dangerous for inhalation, ingestion, and contact. Next slide, please. When we looked at lead-210 in the greater St. Louis area, we took more than 500 samples, 540-ish. There were only 4 samples that were higher than that sediment sample from the Jana School, and 2 of them were actually from the HIS site, the old Hazelwood interim storage site, where we're looking at original material from Mallinckrodt and Cotter. And there are pavement sediment samples taken at the same time from other locations, St. Cyn Park, Duchesne Park, St. Ferdinand Park, that I visited in the days after I visited the Jana School. And their lead-210 numbers and all the other numbers are substantially lower. And Jana schools are rooftop samples. That is, they have roof drains. We tested those. If it's airborne fallout, it should also be in the roof drains. Those numbers are less than 5 picocuries per gram. So it's not like there's fallout only coming on the kindergarten play area. It is what the ATSDR and the EPA say is happening. When the creek overflows its banks, it leaves Mallinckrodt material behind that we can do testing on and see using standard methodologies. Now, we've had a lot of individual details, but the issue really is the preponderance of evidence, multiple lines of evidence talking about this. And yes, it's very true that we have repair mechanisms for dealing with the DNA strand breaks that can result in eventual mutations. And if you get enough mutations in a cell, you can actually have a cancer event that begins. And we actually, I think the number, Lee, is about 10,000 single strand break repairs an hour for an adult. I think it's for the 170-pound REM phantom, but the issue that we have is these are children. What's their nutritional status? What's their family income? Are they getting the right food? Are they getting medical care? Is their body repairing those strand breaks at the same rate as the NRC's, average white man of 170 pounds? We don't know that. I'm going to guess, I'm not a policy person, it's potentially a good deal less. So we have to consider the population that it's being exposed here. I think I have enough time, yes, to talk about some of the individual numbers that went through. Negative results. Radiation tests sometimes give negative results. If I test something if I have something that has no radioactivity in it, I test it, it can have a negative result, it can have a positive result. But if I test it an infinite number of times, on average, it'll be 0. In real life, we don't have the money to test it an infinite number of times. So we test it once or twice or 3 times. Sometimes we get a negative result. It means we didn't detect anything. The negative number that's generated, according to EPA's description about what to do with negative radiation results, is entirely unreliable. It's just a non-detect. It's not a real number. If we have a -2 sample and a +1 sample, the average isn't -0.5. It is a non-detect. It can't be less than 0 unless we've discovered antimatter and Nobel Prizes away. So the technical issue isn't the big thing here, because technically we seem to be on the same ground. Dr. Lewis brought up the idea of potassium-40, Dr. Sobotka as well. Potassium-40 is a natural material. It is a beta emitter, among other things. The radiation from potassium-40 from bananas is not important in our discussion. If you eat potassium salts, what happens? You excrete more potassium. We're homeostatic. You can't get a dose from a banana. You can't get a dose from a lima bean. You can, however, inhale or ingest a particle. Can we? Next slide. Next slide. You can inhale or ingest a particle. And if it's an alpha emitter, the isotope we're really focusing on, and the isotope that's diagnostic for Mallinckrodt waste, if it's internalized, those alpha emissions deliver their energy directly to the cell and to the nucleus. These are some wonderful images showing plutonium oxide, and the alpha tracks within the tissue of the target organism in this experiment. And this is really important because does anybody know the number of hits by an alpha particle to the nucleus of a cell that it takes to kill it? One of you guys must know, right? How many? 1. One. One is enough. Because one alpha particle can theoretically ionize tens of thousands of molecules, including DNA molecules. And it exceeds the repair capability of our DNA. And if that material is internalized in the lungs, or internalized in the intestines, or anywhere else, we run the risk of that individual exposure resulting in a cancer. It doesn't always do so. It mostly doesn't. But your risk increases in a linear fashion with no threshold below which it's completely safe. Next slide, please. What are we doing now? Well, one of the things we're trying to do is to look at individual materials that are close to children's lives. So we are trying to do a population study of the radioactive particulate matter that contains thorium related to Mallinckrodt that we can isolate from children's shoes in Jana and other schools in the area. This is something that we did in Japan after the Fukushima accident. This is something I've done with people who work at Chernobyl in Ukraine, although they're busy now and hard to email. And this is definitely an area of research for us because, again, we're not so much interested in the picocuries. We want to know how the energy is delivered to a cell, period. And in fact, we do most of our work in RADs, not REMs, because RADs are energy that we can measure, and REMs require knowing a lot more about the person, and I ain't that kind of doctor. Next slide. As we know, as the Army Corps tells us, when Coldwater Creek overflows, it deposits material into its floodplain where it is tracked. We can find those radioactive microparticles. We can actually photograph them individually. We can see the percent composition of elements that we know are radioactive. And we can convert that into doses absorbed energy in rats. And some of these individual particles, they cook around 5 to 6 rads a month at the cellular level. Last slide. The blue are the parcels that flood from Coldwater Creek. As I said, there are 14 different public schools that are in that blue area or on those individual parcels. There's nothing unique about Jana in our region. All these other places suffer from the same problem. We're spending a great deal of money to try and remediate this material, to recover it. We know it's out there in the environment in Coldwater Creek and, of course, Westlake Landfill. And the data from standard methods that we share is telling us that we can provably find this material that's being tracked in by human activity. And we understand that children are they're both more likely to track in this material. We know that their doses of dirt and dust from hand to mouth are higher, and they're more susceptible. And even within that group, there are some groups in the greater St. Louis area that are more susceptible because they don't have the same quality of medical care or the same quality nutritional status. That's why this work is important. That's why I will never be the last word on this. And that's why I'm extremely supportive of efforts to have comprehensive testing and cleanup where required by the Army Corps and other federal agencies. And I just want to thank the university again for having me here today.
Testing, everybody hear me okay? Yep, I think so. I'm John Rankins. I'm with the Corps of Engineers. I'm a senior health physicist with the FUSRAP program. I'm going to go over some of our background as quickly as possible. We do have a lot of content and get to Jana Elementary eventually. We'll be tag teaming this first presentation with Chuck Finkenbein, who's a health physicist with Leidos, and Brad Wilson, our laboratory manager for our radiochemistry lab, will not be doing a presentation due to time constraints, but he does have all the materials available online, the presentation, and everything at the tables. If anybody's interested in our laboratory processes. And Randy Hansen, another health physicist with Avicii. So we're going to go over our record of decision and how remediation goals are established, sampling and survey methodology, summary of Jana Elementary, the school structure survey report, which has now been finalized and published. I believe we do have hard copies here available. No. We do have a couple of hard copies available. Not all 466 pages, but the bulk of the report is available for viewing here today. It is also available online. We will have a discussion on lead-210. As everybody has previously discussed, we will discuss our testing methodologies and findings. And Randy will follow that. We'll end it with some modeling software that we use to calculate exposure, dose, risk to hypothetical exposed individuals, such as students at a school. What is a record of decision? Our ROD is a formal decision document developed for the public that identifies the preferred alternative and explains the remediation plan and the rationale for cleanup of a Superfund site. To gain the opinions of all stakeholders involved with the site, comments were addressed and incorporated into the record of decision, which was approved and finalized September 2nd, 2005. Applicable or relevant and appropriate requirement and remedial goals, otherwise known as ARARs. You hear us talk about ARARs a lot. What does that mean when it comes to cleanup goals and cleanup criteria? The short answer or relevance to our project and to Jana Elementary is our ARRs for North County are 40 CFR Part 192, Subpart A and Subpart B. These establish basically the radium-226 concentration shall not exceed 5 picocuries per gram above background in the top 6 inches of any soil and 15 picocuries per gram above background in the lower 6 inches of soil, averaged over any 100 square meter aerial average. The other component of that is when you have a multitude of contaminants of concern, when you have more than just radium-226. So we have radium-226, thorium-230, U-238. 10 CFR 40 Appendix A Criteria 6.6 applies for that type of scenario. That requires that a byproduct material containing concentrations of radionuclides other than radium in soil and surface activity on remaining structures, like a Jana school structure and all of its contents, that the total effective dose equivalent exceeding the dose from cleanup of radium-contaminated soil to the standard benchmark dose, and must be at levels which are as low as reasonably achievable. I want to emphasize ALARA, as low as reasonably achievable. That will be a theme throughout our development of our remedial goals through our comprehensive process of writing our record of decision and coming up with a selected remedy. It's all based on the ALARA principle. The standard benchmark dose radium-226 remedial goals in soil equates to 19 millirem per year. So nothing can exceed 19 millirem per year, period. Soil remedial goals. So our record of decision is very comprehensive. It involves remedial goals for many different COCs, not just thorium-230 or radium-226 or U-238. There's surface soils, there's subsurface soils, there's soils on structures, there are metals, some of those rare earth metals that the gentleman before me discussed. Those are also contaminants of concern, depending on where you're at in North County. The U-238 remedial goal is established using U-238 as a surrogate for all uranium isotopes, which would include U-234 and U-235, and certain uranium decay products. The surface soil RG for U-238 is calculated to be 81 picocuries per gram. When you do the math and do the approach, U-238, the number comes out to be 81 picocuries per gram when used as a surrogate for total uranium. The U-238 remedial goal was lowered to 50 picocuries per gram to account for the decay products of that parent, U-238. This is an ALARA principle. It's as low as reasonably achievable. So it's even lower than the risk and dose-based methodology. And although the U-238 concentration equating to 15 picocuries per gram of radium-226 is 150 picocuries per gram for subsurface soil, we stayed with the 50 picocuries per gram for U-238 in subsurface soil. Again, another ALARA principle applied to the remedial goals, which is very health protective. So we could have much higher remedial goals, but with stakeholder input, the community comment period, these are the types of things that go into developing these remedial goals. And as I'll try to speed through this, because we have a lot of content to go through that's very important. And I don't want to, spend a lot of time on these things, but we have remedial goals for each individual radionuclide. We also have to sum those ratios up, and that has to be less than 1 over any 100 square meters. So you can have radium-226 content in an area on a property that's less than your individual remedial goal. That doesn't mean that it's necessarily below our remedial goals, and we can release it. We might, we have to take the fraction of all of the contaminants of concern into consideration, and that will determine and dictate where you might need to do removal actions. We also have sediment remedial goals. I left that out earlier. Another set of remedial goals. This is for sediment below mean water gradient. So think of the sediment below like average base flow of water in Coldwater Creek at any given time. The material under active water flow. Those are 15, 43, and 150 for U-238. Again, these are ALARA principles. Now I'm going to have Chuck Fakeby come up. He's going to finish this section of the slideshow out. He's going to discuss the soil on surfaces, DCGOs.
Put down for moving forward. Okay, John talked about soil DCGLs, and I'm going to talk about the structure and how we came up with those limits. So again, on another LARA that John talked about, instead of 19 millirem, we used 15 millirem to come up with our limits for structures for North County sites. We looked at 4 different type of receptors during that evaluation for industrial worker, a renovation worker, a building resident, and a post-demolition on-site resident. The building occupancy industrial scenario represents the reasonable maximum exposed visual and was the basis for our DCGLs. And we use ResRad build version 3.1 to calculate those values. And Randy Hansen's going to talk about that later on in detail about our modeling. Here's the RGs for all of our principal nuclides that are listed in the rod. Thorium-230 is 6,900, and radium-226 and lead-210 are all listed on here. These are all the main nuclides that have limits. So determining an alpha surrogate DCGL is what we set out to do. So we looking at total activity. You have an equation for 1 divided by the activity fractions divided by each of those DCGLs that we listed in the previous table to come up with the total activity number. And here's an example where all the activity fractions for all those nuclides we listed in the table divided by their DCGL. So the total activity would be 6,704 dpm per 100 centimeter squared. Decay chain emissions is all the 3 decay chains that they showed in the previous presentations. And it shows in red are the principal nuclides that are listed in the rod with the DCGL values. And those have long half-lives. That's why they're listed, shown in red. And then all the daughter products under each one of them are very short half-lives from minutes to days. And those are the daughter products of the main nuclides. Also, you see over here, they're alpha, whether they're alpha or beta emitters, and down to the stable nuclide for each of those 3 decay chains. And for example, we'll use actinium-227 because I'm going to talk about that on the next slide. There are 3 beta emitters that are involved in that chain, and there's 5 alpha emitters before it gets down to a stable nuclide. Some of the beta, we have the energy listed out to the side, like actinium-227. You see there the beta is 9.9 keV, so we wouldn't be able to see that with our instrumentation. It's just not a strong enough energy. So now determining the alpha portion of the activity fraction, activity fraction of actinium-227, which that comes from all the samples that we collected in Coldwater Creek, and looked at those results for hundreds of those samples and come up with an activity fraction, how it's divided up between each of those. Then we take the number of alpha emissions divided by the number of the total emissions, which is alpha plus beta, and it gives us the activity fraction on the end there that's associated with actinium-227. This table lays out the number of alpha emissions, the number of beta emissions, the total emissions, and then it has the alpha portion of that activity fraction. And you'll see right here, about 92% of our activity comes from the alpha and only 8.5% from beta, which some of those we can't see with our instrumentation based on the energy. So that's why we're looking principally at alpha, our rod DCGLs. But when we're going to talk later on about when we take measurements. When we did take alpha measurements, we also collected beta measurements as well. So you take your 91.5% times that 6,704 that we had, and it gives you 34 is what our alpha DCGL would be. And we reduce that down to 6,000 because that's a nice even number, and again, to instill the ALARA principle. We had activity fractions from the feasibility study that we, before we had all of our sampling on Coldwater Creek, we used those activity fractions, and it was even a lower DCGL because we didn't have as good of activity fractions. But we used this 2,800 DPM, again, to be ALARA. When we sampled the school, we used 2,800 to look at our alpha results. So after we have our RGs, we have all the soil RGs, we have the alpha limits, we have to sample and survey. So to do that, we have to develop a work plan. So the kind of things we looked at aerial photos, channel improvements, historical sampling data. We actually go out in the field and walk down the property and look at tributaries, drainages, low-lying areas, depositional fill areas. And we identify areas that we want to sample and how deep we want to sample based on all that information. Here's an example of what a figure in our work plan would look like, where we have grid sampling out here in the floodplain area. And this is actually part of Jana School right here. The creek corridor, where we have much tighter grid spacing in here, because that's where there's a lot more potential to find things. And we have to do bias sampling. You can see that the tributary that runs into the creek, we'd sample bias all the way up the creek. And we've sampled bias on a lot of these different things we talked about up here, the different kind of features that we found. Prior to going out sampling, now that you have your plan, you have to get right of entries. And you can imagine there's hundreds of properties, hundreds of people. So it's quite an effort to get access agreements to get on the property to start with. Then you have to do utility clearance, brush clearing and marking paths and stairway. For example, like clearing, this is a cold water corridor. You have to clear all that brush. There's an example where you have to get down the creek banks. You have to build stairways. You have to clear paths. It's another monumental effort to do those things that really takes effort. Sometimes people wonder why does it take so long. These are some of the reasons. And then we have to go out and pin the points with our GPS system so that they know where to sample. Soil sampling methodology, when we collect our samples, for surface samples, we just use a spoon and a bowl and collect it. When we're doing subsurface sampling, we'll use a hand auger, which is shown right here, or a drill rig, which is an example over there. And you can see, like when we're out there sampling, there's not a lot of PPE that you have to wear and protective clothing. We wear gloves to protect our hands. And if it's real muddy and dirty, we'll wear booties or put on Tyvek to keep you from getting mud all over you. And when people leave the field, we scan ourselves after surveying. Here's another example. This is from Coldwater Creek, and we have hillsides that are covered with rocks like this. You also have asphalt and concrete coverings. It's quite a chore to get and sample underneath that, as you can imagine. So we use things like, we have a jackhammer. We use that to get underneath these rocks and get sampling underneath to make sure there's nothing underneath the rocks. To do sediment sampling, again, it's quite an effort. To get out there in the deeper water, we have to have a sampling platform. We have two different types. We have a bigger sampling platform. This is one of our smaller ones to get out and sample the sediment in deeper water. And in shallow water, we sample here. And for those, we use either a hand auger or typically a sediment sampler, which you see here using sediment samplers to get samples of the sediment under the water. Once we collect our samples, we take them back to what we call a sample screening station. And this is kind of an example here where you see the yellow covering on the table. That's where we would take our samples to. The instrumentation there, we scan it and mark that down in our logbooks. A geologist or a soil scientist will inspect the soil and see what kind of soil we're running into. Did we get down to the right layer that we're looking for? Any changes in the layer? And then we log everything in logbooks. On the other side of the table, you see a log in there. In the cans, that's where we put our samples in to take them to the laboratory. All that takes place at that table there. And every day we go out there, we got to set this up and take it down, set it up, take it down when we go to lunch and come back. So that's quite an effort too sometimes. Now our surveys. So we talked about alpha and beta in the previous charts, but there's also the gamma as they talked about earlier in the day. For gamma walkover surveys, when we're surveying soil, we look for gamma. And here's a crew that's walking over with a sodium iodide 2x2 detector. And the yellow instrument to the right is our GPS system that logs a reading every second. And it also logs coordinates. So if you were to find a high reading, you have coordinates that can lead you back to where it is. When walking over, they listen to the sound. And if they see anything elevated, they'll stop and pause. They'll put a flag there that we can come back to investigate. And the good GPS system, we can make color-coded figures when we come back based on the scales that we want to look at. And we use it generally, a blue or green color is background. Blue is background, green is the upper end of background. And when you get up to colors like yellow, red, or black higher than that, those would be places we'd go back and investigate. And you can see Jana School here. That was all on the surface. Those are the type of readings we see where it's all blue generally. For structure surveys, we use a Ludlam 4389. That's what we get our alpha readings with. And as I mentioned, when we take our alpha readings, we've also logged in a beta reading as well, which we use in the report. And here's an example of surveying a swing there at Jana School. And we use that detector when we surveyed inside Jana School, and the asphalt outside, the concrete, all the equipment that we surveyed, that's the instrument that we generally used. Along with this is the floor monitor. It's a gas proportional gas. It measures for alpha and beta as well. And here's an example at Jana School. We surveyed on the first floor 100% of the accessible area of the floors, because if anyone was tracking things in, that would be the most likely place it would be. And then we surveyed 2 meters squared around all our other measurements, and also bias and scan measurements at some of the dust sample locations, and also by doorways where people would track things in. So once we collected all that information, we have come up with a report, which they mentioned is available here and online now. There's also a tier online to get that report. In total, we surfaced 13,000 square feet within the school and outside the school. There was 461 fixed point measurements for alpha, and that also included the beta that we logged. And we used that detector that we just talked about. There's 461 smears. So at every place we went and took readings, we also collected a smear to see if there was anything removable in the school. We also went and bias location samples. We collected 5 indoor locations where we found dust. There was not a lot of dust in the school that was easily achieved. It was pretty clean. So you'll see later on some places in the next presentation where we took some of those samples. We also collected sediment samples outside. One of them is that location on the playground. We got comparable numbers for the Lit 210. The other 2 contractors found as well. And the bottom line of all these RGs that we talked about, the rod, is it safe for people? So the Jana School dose and risk. And we have to make sure that additional lifetime risk to any individual is less than 1 times 10 to the 4th, and we don't exceed that 19 milligram a year. So the RGs, by meeting those, we're going to meet our risk at the end of our dose. So those help us to make sure that we meet it, and then we finalize it in a report. So here, the 1 times 10 to the minus 4th comes, it's listed in this National and Hazardous Substance Pollution Contingency Plan. And here's some examples of death that are many times higher. A vehicle crash, you're 90 times more likely to die in that than here. And here's some other. There's a poster out here that has the same thing, but it shows you the circular risk range is the red here, where it's acceptable risk that they've determined is acceptable. And make sure below 1 times 10 to the minus 4th, and normally we're well below that by being a LARA and staying well below our limits. And we also put on here Coldwater Creek. It's down here like 1 in a million, 1 to the minus 6. If someone were to play in there an hour a week, a child or something during the day, it would be a lower risk than that. So our final survey results, we have, we met unrestricted release for the school. Our limits are well below the results you expected range of natural background levels. And one of the things we did with our readings, we didn't subtract the material background when we take our structure readings. So there's also background material that you get from just a piece of granite or ceramic tile. We just didn't include that when we looked at our DPM. None of the measurements for removal activity exceeded MD's minimum detectable concentration. So every smear that we took was below MDC in the building. And they were very low levels, way below what our limits are. All dust samples were 1/11 of the limits for soil. So we didn't have a limit for dust. We compared it to our soil limit. And as we talked about earlier in the previous presentation about the students, we actually look at a student receptor in the school, a staff receptor and a suburban resident. So we looked at how many years each of those would be there, how many days of the year they would be in the school, and how many hours per day. And we use very risk and dose estimates are designed to avoid underestimates. So when we're doing that, we put in all kinds of conservatism into that. And if you want to see those, they're in the report that list out all the type of conservatisms that we include in there to make sure people are safe. And this is an example, since we really didn't find anything above background activity in the school. This is really the dose and risk from natural radioactivity. And since we didn't subtract it out of our background readings, there is some that shows up here. Here would be our limit for dose, and there would be our limit for risk. And then the comparison of what we got on our very conservative health and dose and risk assessments. And the bottom line is that the surfaces of Jana structures meet circular protectiveness requirements are consistent with background levels. No evidence was identified that radioactivity from historical MEDCA operations has been relocated from the areas with MED to these structures. And in the next presentation, which is lead-210, they'll go into a little bit more about that.
Before we get the other slideshow up, we do have the instruments. We have all the instruments here, operational. If anybody cares to look, we do have a table set up. The same instruments we use to test Jana Elementary, we have here, and it is very important to recognize that we did not, all the different types of materials in the school. We just included that background, the material background, in our dose and risk calculations. So they're biased high is another way of saying that. They're very health protective, conservative, biased high, because we went ahead and included the material background in our results. All right. I was afraid of that. This is the juicy stuff here. Lead-210. So some of this is kind of redundant from the previous slideshow. We did go out and collect radiological data from the structure surfaces, as you have seen. We also collected a large number of additional soil samples. Lead-210 occurs in nature. I think we beat this to death at this point. Lead-210 beta decay is a beta emitter. It is detectable when we're doing gross alpha and beta measurements. A fraction of those alpha and beta detections are from lead-210 or polonium-210. It's just a very, very small fraction as compared to thorium-230, which is about 85% of our makeup of our contaminants of concern. Of all the measurements we talked about earlier, 461 fixed point measurements, 461 smears. They're very relevant to lead-210 itself because, like I said, lead-210 makes up a percentage of that gross alpha or beta and beta measurements. Of the fixed point measurements, as expected, 99.7% of them were within 3 standard deviations of the mean background values. Essentially, as you would expect, they're all within background range. All swipe measurement results were below the minimum detectable concentrations. So every time we took a fixed point measurement, we took a swipe to find any removable dust that could have been contaminated. All of those were less than detectable limits. Soil samples. All the soil samples and all the fixed point measurements, again, they apply to lead-210 as well. Although lead-210 isn't a primary contaminant of concern, it is still a contaminant of concern. A total of 1,211 samples of surface and subsurface soil were collected from 223 locations on Jana's property. Of the 1,211, 790 of those were additional samples that we collected in response to community's concerns regarding the Boston Chemical Report. So we had already been out years ago and we had done testing. We did gamma walkover surveys of the 10-year floodplain. We had collected samples, roughly 320 soil samples on the property We identified the contamination that exists. Nobody questions that the contamination is within Coldwater Creek banks. But we collected 790 further, soil samples outside of, above and beyond our conceptual site model. We went up gradient to the school from one end of the parcel boundary to the other. Soil sample data sets. We split the data sets, the soil samples, into 3 sections. Coldwater Creek, kind of the Coldwater Creek bank, one end to the other. The woods or tree lined soil data set, and then the clearing soil data set, which is kind of the open field back behind Jana, and anywhere a student or staff could exist on the property from a day-to-day basis. Radium-226 results comparison with background. We compared the radium-226 values against the background data set using the Wilcoxon-Mann-Whitney comparison test. The test conclusions with a 95% confidence interval that 1, the clearing soil data set was consistent with or less than values from the background soil data set. The background soil data, here you can see the background values for North County here. This is the surface background data set. The clearing data, the areas that are used by student and staff and utility workers, those are at or less than these background values. And again, it's not like a number, a single sample point. It's the whole data set that we're comparing. You're comparing 2 distributed data sets. So that's why we use the Wilcoxon-Mann-Whitney comparison test. If you want more information on that, Google it right up, okay? We could sit here for hours to talk about that. We don't have time, so. The Woods and Coldwater Creek corridor soil data sets were greater than the values of the background data set. As expected, we found contamination in the Coldwater Creek corridor. We found a couple of individual samples in the Woods area that are above background, but below our remedial goals. Indoor dust and outdoor pavement sediment samples. Some of these pictures will probably look familiar. We did collect 5 indoor dust samples, and we did collect 4 outdoor sediment samples. Okay, here, unfortunately, like this represents why we're even here today, why we have gone through extensive testing efforts because of this clump of dirt out here on the courtyard next to a playground. That's it. There's a storm right here. This material has collected over, during storm events, as we've talked about before, which I'll get to, how did this lead-210 get here? We found 44 picocuries per gram of lead-210 at that location. SCI found the same thing. Mr. Kaltofen found the same thing. We also took other pavement sediment locations. There's a storm drain right here, number 3. We didn't find any lead-210 there because it drains properly, just like a downspout would. When you have a downspout, it disperses lead-210. It doesn't accumulate there. Location number 2 here, pavement sediment sample. There is accumulation of stormwater runoff, right? And as you can see in that picture, there's about 10 picocuries per gram of lead-210 at that accumulation area. So anytime you have low-lying areas at a parking lot or a courtyard or any kind of structure, you're going to have this type of natural process where rain and snow and weather wash out lead-210 from radon gas. It accumulates on a large enough surface area, but I'm talking about that way too soon. We also, remember, we collected 5 dust samples inside the school as well. So it's a school, it's very clean, it's cleaned every day. We collected 19 swipe samples in addition to the 5 indoor dust samples. When we say a dust sample, we have to get enough mass to actually put on a detector and analyze it. So it was 5 is like the most amount of dust samples we could get indoor to analyze for thorium-230, radium-226, and U-238. In addition to those, we collected 19 swipe samples from less disturbed and dirtier locations in the school. Things like the boiler room, closets, overhanging, metal structures, piping, ductwork. Those were very dusty. There were ceiling fans in the kitchen that are used to cool the workers. Those were extremely dusty. We didn't find anything. We didn't find any lead-210. We didn't find any uranium, thorium, or radium. Bottom line. The average results for these samples were less than the natural background average for North County when comparing to the soil background values that we looked at earlier. All lead-210 swipes were less than the minimum detectable concentration. We did swipes. We submitted them to Eurofins in Earth City. They were analyzed via liquid scintillation counting and all less than MDCs. I talked about earlier, 2 of the pavement sediment samples had lead-210 results that were approximately 10 and 40 times higher than the results for radium, thorium, and uranium in those same samples. So where we found lead-210, we also analyzed for our primary COCs, radium, thorium, and uranium, and there were no presence of any of those radionuclides in those samples as well. So the lead-210 kind of stands on its own. Where did this come from? Where on earth did the lead-210 come from? Is it from our stuff? Is it from radon gas? Did a student or a person track the contamination into the school along, at some point in time and tracked enough material from the bottom of Coldwater Creek to the courtyard? The school pavement is located on a knoll approximately 6 feet higher than the highest recorded flooding ever at that property. That occurred in 1957. The school was built in early 70s. I don't know if we have an exact date on that, but here's I'm sure most of you remember last summer, July 26th, we had a historic 1,000-year storm event, record flooding along Coldwater Creek. Here's a picture of that day, standing on the pavement next to the playground. That courtyard does not flood. Where we found the lead-210, it's never been flooded from stormwater or from floodwaters of Coldwater Creek. Okay? Ever. This is the worst flood possible. Hopefully, God forbid, we don't have another one of these this summer. So we can rule that out. This is what it looks like. There's one of our engineers standing literally on top of a contaminated area that we will be remediating this summer. to give you some context of how difficult and inaccessible this area is. It would be very unsafe for a child, an elementary student, or staff, or anybody to be accessing this contaminated piece of land in Coldwater Creek. The steeps are banked. The contamination is subsurface, meaning it has clean soil on top of it, not to mention all the debris and vegetation that is on top of that as well. So the likelihood of somebody tracking contamination on their shoes or clothing into the school, or even on the other side of the school, is extremely unlikely. And this worker is approximately 6 foot tall. That's a 20-foot slope, steep slope, and just that gives you some context of what we're dealing with. Like this summer, Robin and Phil, they'll be out there removing all that material. We also looked at radon emissions from how much radon could possibly have emitted from that contaminated area and made its way over on top of the school and beyond, and dropped out lead-210. So we did a CAP 88 model, which Randy's going to talk about next. The additional concentration of radon, theoretically, and airborne decay products reaching the school from Coldwater Creek corridor is 1.2 e to the minus fourth picocuries per liter. The average outdoor background radon for North St. Louis County sites over the last 10 years is 0.2 picocuries per liter. So essentially, no radon is going to fall out on top of the school. I think we've kind of beat this home. Radon 222, radon decays to atoms that attach to particulates in air. They are washed out in precipitation events. Things like pavement, parking lots, sidewalks, rooftops accumulate sediment that radon decays, to lead-210. These natural concentrating processes for pavement sediment have been found to have background lead-210 concentrations as high as 71 picocuries per gram. I know Lee talked about 30 to 40 picocuries per gram. There are plenty of published studies that they use lead-210 as a tracer. Hundreds of studies every year. Lead-210 is used as a tracer for erosion rates and things like that. It's very common to find 70 picocuries per gram of lead-210 in the soil. But we can argue about where it came from. Is it MEDAC waste? Is it not? Is it natural? Doesn't matter. What's the risk? At the end of the day, what's the risk to the kids or the staff or possibly a resident? Somebody might want to, if it's not going to be a school anymore, maybe it'll be turned into condos or somebody will live there. What's the risk? There it is. The cancer risk and toxicity comparisons. The risk is less than 1/200th of the circular risk standard for protection of human health. That's to a student that Chuck talked about earlier. How many hours a day? 11 and a half hours a day for 6 years, full-time student. What is the toxicity? So that looks like an incredibly small number because it is. That is comparing to something that we all are more familiar with, and that would be lead-based paint. So the TSCA standard for protection of children at a playground is 400 micrograms per kilogram. The amount of lead that we have all come up with, 44 picocuries per gram, roughly 40 to 50 picocuries per gram, That's the mass equivalent, 1/600 millionth of the TSCA lead-based paint standards for protection of human health. That's all that really matters. That's why we say the school's safe. There's nothing, we haven't found any contamination. Haven't found anything above normal background. That's it. Thank you.
Okay, hello everybody. While she's getting that up there, my name is Randy Hansen. I'm a health physicist working on the St. Louis Foods Rep program. I conduct dose and risk assessments, and kind of what John finished up with on that last slide there. What I really do is, we've collected all of this data, right? We talked about 213,000 square foot of sample or surveys that we did at Jana School. That, when I think about the size of my home compared to that, that's a lot of data that we've collected to determine, do we have risks out there, right? But the bottom line, you can't do anything with that data. The data doesn't really tell you anything unless you take that data and use it to determine, okay, how bad is that for me, right? Here's a number, but how bad is that for me? I see the donuts on the table over there, right? If I eat one donut, it's probably okay. But if I eat the whole thing of donuts, well, at some point, it becomes a hazard to me, right? And that's what we're looking at when we do dose and risk assessments. We take a look at the data, and then we want to find out how bad is it for me. So I want to cover some of the modeling software that we use on the Foods Rep cleanup project. Next slide. So there's a couple of reasons we use modeling software. Number one, we use it to develop our cleanup goals, like they discussed earlier. We also use modeling software to assess that risk and dose to specific receptors from radioactive material that they may be exposed to. Next slide. One of the things we run into when dealing with radioactive material and doing risk assessments, especially the type that we have, is this radioactive material is found in background. You've been hearing that quite a bit, right? The uranium, thorium, radium, it's already it's in soil everywhere. And when you take a look at the, what the risk associated with just natural background radiation, we take a look at that surface data set that John talked about. Here's your average picocubic concentration. When you run a risk model for that, you end up with 1.8 E-4 risk for just a resident with that in your backyard or the backyard of any home in the St. Louis area. Okay, and that's somebody without a garden. If somebody has a garden or the resident farmer scenario, you end up with a risk of 2.8 E-4, which is already above the circle of risk range. The high end of the circle of risk range is 1 E-4. So, when we try to establish these remediation goals, when we originally try to establish them like EPA wants us to at the low end of the risk range, it's kind of hard to do that. So we have to kind of modify our process in determining what's an acceptable risk range. And that's all the RG stuff. The next slide is just a recap of the RGs that they talked about. Soil, sediment, RGs. We talked about remediation goals on structures with the DCGLs and all of that, and how some of the background on how we got to that. Well, the next slide, there's a couple of different, when it comes to developing remediation goals and doing dose and risk assessments, there are several types of modeling software that can make the process go smoother that we like to use out there. Many of you may be familiar with the EPA PRG software. And this, this slide gives you a visual of what those EPA calculators look like. If you've gone on the website, this is what they look like. They have a whole bunch of different programs that you can select up there, whether you want to do a soil PRG. I'm sorry, PRG is preliminary remediation goal. For this one, for the structures, we picked the BPRG, which is building preliminary remediation goal. On the next slide, I want to talk about the RESRAD family of codes, because there's sometimes a confusion. People look at us and say, or at the Corps and say, why aren't you using the EPA PRGs like everybody else does for chemical contaminants and things like that? because we use ResRad, and it's sometimes it's confusing. ResRad set of codes was developed by the Argonne National Laboratory for the Department of Energy Nuclear Regulatory Commission. These codes, basically, you can use them to model dose and risk to receptors living on top of a contaminated site or somebody who might be right next to a contaminated site. For this assessment, we looked at the ResRad build, which is someone inside of a building. You can model dose and risk to that receptor inside of a building where the inside of the building may be contaminated. On the next slide, I just wanted to kind of put a comparison of the different user interfaces. Over on the left is a ResRad build user interface, all the different parameters you can put in there. You can see the 3D model up there of the room where the floor is contaminated, and then I've got sources set up on each individual wall, and then the receptor is located right in the center of that room. Over on the right is a couple of, here's what the user interface, what you will see for the building PRG code. All right, on the next slide. I want to do a little comparison because one thing users need to be aware of is if you try to use these codes using only the default parameters, you most likely get wildly different results because of how the codes were put together and the goals that the EPA was trying to do versus what the DOE and NRC were looking to do. However, if you ensure that both sets of codes are using the same parameters, you're going to end up with the same output. So in an example here on the screen, I used the thorium-230 structure DCGL just as an example of 6,900 disintegrations per minute per 100 centimeters squared, which is approximately 31 picocuries per centimeter squared, which is a surface contamination. So, right, the dust is in there because it deposits on the surface. So we're talking surface contamination. And I use that as an input to both models. For ResRad build, I used our structured DCGL model, our DCL worker scenario, where those parameters can be found in the record of decision. For the BPRG, for this example, I just used the default parameters that you get on the website. Okay, the only thing I adjusted was there's an area factor you can select on that, and I used 200 square meters, which is the closest equivalent I could find to our parameter that we use in the ResRad, the worker scenario in the ROD, which is 180 square meters. I also used the most current ICRP, dose conversion factors and slope factors for dose and risk, which come from ICRP 107. All right, the next slide. When you compare the outputs for these two models, you can see up top there, there's orders of magnitude difference between the ResRad build and the EPA BPRG results. 1E minus 4 for res build was a risk, and that came predominantly from an external dose, and 3.4 e to the minus 2 risk from EPA's BPRG. And both of these peak risks occur at, from start year 0, they occur at year 8,930 in those models. I also got about 17.4 millirem per year from the ResRad build model. I was not able to get an output from the EPA code. You have to use a separate code. It's not the BPRG. You have to go to the DCC codes. I went to that and tried to do it for a resident, and I was not able to get an outcome from that. I could get one for, you can get one for a resident. I could not get it for a worker, so I was not able to get an output for that. But there's just, that's the thing you got to look for in these codes, is making sure you're talking apples to apples when you put in all these parameters. All right, next slide, please. So why are those results so different? Because they were quite a bit different there, 2 orders of magnitude. Well, ResRad build calculates a realistic source inventory for what's actually going on with the radioactive source. Because the source was assumed to have migrated onto the structure surface from surrounding soil, some of that source is assumed to be movable, like dust, right? It's going to get resuspended into the air. Some of it's going to be removed through ventilation systems, and some of it's going to be inhaled or ingested from the receptor. The ResRad program accounts for this, whereas the BPRG calculator its default parameter assumes that there's no source removal except by just natural decay. And you can see that the default dissipation rate for BPRG is set at 0. So at the peak, or at the time of peak risk for BPRG, the parent decay activity is calculated, and then all of the daughter products are just assumed to be in secular equilibrium or the same activity as the decayed parent. And this could, or this might, overestimate actual risk and dose at that time. Next slide gives you an example of what I'm talking about. I actually used ResRad with 100 picocuries per gram of thorium-230 in soil, just to kind of show you over time what that decay of your parent is. Thorium-230 at your 8,930, okay, was down to about 90% of its original activity, 90 picocuries per gram. And we talked to one of the earlier individuals was talking about what happens in those lower buckets. That's the buildup. If you take it from 0, what's that buildup from the drip? Radium-226 in this case is the next daughter product down for thorium-230. And you can see that at your 8930, you only have about 1/6 of the buildup of the original activity or the parent activity. And you can see over on the right-hand side of the screen, EPA BPRG assumes that the daughter is the exact same or secular equilibrium. All right, so there's something going on there. ResRad programs account for, let me get into, ResRad accounts for that movement of the material, removal of it through ingestion and inhalation, and also a proper buildup. Now you can't do a straight comparison here because the ResRad graphs also includes source reduction through migration, but it can give us an idea of why there's such a difference in those risk results, okay? Next slide, please. When it comes to source inventory, another thing I wanted to demonstrate is that while ResRad build accounts for normal migration and reduction of the original source, okay, BPRG default assumes that none of the source is removed, like I said earlier. In fact, the BPRG calculator assumes that the same initial concentration is available for ingestion, okay, over that entire 25-year duration. For this particular assessment, BPRG calculates that about 25% of the entire source that was deposited on those surfaces is actually ingested by the receptor in that 25-year period. Now I got a 6-pack of Coke up on the screen, right? And everybody's like not listening to me on that. They're like, why has he got a 6-pack of Coke up there? So let me tell you about that. It's an analogy because I want to explain what BPRG calculator is doing. It's like saying if I start with a 6-pack of Coke and I drink some of it each day, doesn't matter how much, the next morning, I start out again with an entire full 6-pack of Coke, okay? And this happens day after day for the entire 25-year exposure duration. And it's a simple and a conservative way to calculate intake, but it doesn't make sense, and it can and generally does overestimate risk, which is why we saw that difference of 2 orders of magnitude risk between ResRad and the BPRG calculator initially. Next slide, please. So I just want to talk about why we, as the FUSRAP project, use ResRad build and the ResRad modeling programs. The simple answer is this: EPA didn't have a building PRG calculator in 2004 when these RGs were developed and the ROD was signed. That didn't come. BPRG calculator wasn't introduced until 2007. Also, FUSRAP is a Department of Energy program, and the Department of Energy's direction to us is to use the ResRad software. Additionally, we could have used the RAGS equations. RAGS is Risk Assessment Guidance for Superfund. And that's just hand calculations, right, to get it all out. But I think if any of you in here have done that before, it's much easier and simpler to use these modeling softwares, and they do all the math for us, right? It's much better for us. ResRad build assesses both dose and risk at the same time, whereas the EPA calculators require you to input the information separately into two different calculators to get both dose and risk. ResRad build also maintains that more accurate source inventory like I talked about earlier with the parent decay and the daughter buildup. And finally, the EPA calculators are only online and you cannot save the input files. It makes it much more difficult. With ResRad and the ResRad programs, you're able to save those files. You can give them to a different user. They can use them for quality. They can do their quality checks on those. Just makes it a whole lot easier to use. All right. The next two slides I want to talk about. Next slide, please. All right. Well, out of time. The next two ones are Pro UCL and Cap 8A. You can check those out on the slides. I think they're all online. Thank you, guys.
Okay, so we've got a lot of questions here. I'm going to do our best to get through them. And these are in no particular order. We just kind of group them by either, person they're directed towards or topic. So first one is for Dr. Katolfin. How is the radiation at Jana different from anywhere else in the country or for that matter in the world?
Actually, that's a very straightforward answer. What's different about the radiation at the Jana School compared to places outside of Greater St. Louis, particularly North County, is that Jana School abuts a known source of radioactivity, which at the moment is not remediated, and which potentially can produce additional exposure in the future beyond what's present now. And very quickly, what does it mean? For instance, in the last speaker who spoke about ResRad versus the EPA model, one of the things that it means is that in modeling, we are faced with the complexity of modeling what happens every time there is additional flooding, where that source, rather than decaying, is renewed potentially to a level that's greater than the present level. And what's different about radioactivity at Jana School is exactly that since flooding is a major vector of contamination spread, that source may not decay in the usual fashion, but may in fact be restored by added flooding events. That will continue until Coldwater Creek itself is fully remediated. And even if the school staff are doing an excellent job of reducing the amount of dust that is in the school, which has many benefits over and above just radioactive exposure, that continuing flooding will always represent an important difference between what's happening at the school and the other 13 school properties versus the rest of the world.
Okay, we do have a couple other questions, I guess, regarding the flooding. I think part of this might have been addressed during the presentation, but there was concern of floodwater spreading radioactive sediments outside the banks of Coldwater Creek. Has floodwater ever entered Jana Elementary or the playground, parking lot, etc.?
No, the flood, as far as we're aware, the pavement at Jana has never flooded, other than, like a flash flood on the parking lot, not from Coldwater Creek. And Coldwater Creek waters have not flooded the school itself as well. And I would like to add that when flood events do happen along Coldwater Creek, which they happen very often, I will remind everybody, we have removed the source sites. The sources of contamination have been removed from the St. Louis Airport site and the Laddie Avenue sites. There is no migration happening during flooding events or active excavations currently. So, like when we had the record storm event last summer, we went out in response and collected hundreds of sediment samples. And we collected hundreds of swipes. We collected fixed point measurements in response to that one flood event to determine that no contamination is migrating currently. and hasn't since we took over the site to clean up. So when he says things are going to continue to get worse, that is not accurate at all. That is not what we've sampled. We've collected over 50,000 soil samples along Coldwater Creek. We monitor the creek. We monitor the sediment in the creek year round. We monitor the groundwater around our source sites. None of this migration that is mentioned is happening.
All right, thank you. And so just kind of following along again with the flooding, is there a rainwater drainage issue for the Jana School? I think it says Jana School roof that would suggest that lead-210 should accumulate like that of concrete parking lot.
One of the things that happens is obviously there are other parking lots, other places in the area that we've sampled, and I mentioned before that we'd sampled about 540 different locations where we looked at lead-210, and compared to all of the other locations that we sampled, save 4 out of 540, that location we've been discussing so much today was higher than all of those. Although I will say that 2 of the locations that were higher, based on the test data that we have, both came from the former HIS site at Laddie Avenue. These are current samples recently collected where we had lead-210 elevated beyond what we found at the Jana School. And we also found several thousand picocuries per gram of thorium-230 currently at those locations along Coldwater Creek. So I'm assuming this is excluded from the comment that there is no more source material.
Just a comment. In the study I referenced from Baltimore, the number in excess of 40 picocuries per gram was an average of 85 measurements.
Is it possible to have a follow-up question?
We'd prefer you put it in the chat, but since you have our attention.
I did.
Oh, okay.
I did put it in the chat, but I've heard 2 things said about there not being, the cleanup efforts are over and everything's cleaned up from the source location. But so I work near the site, the SLAP site, the airport site, and there is an active cleanup site on the other side of McDonald Boulevard. And during this big flood event last year, they had a car wash onto it, and radioactive signs were put up for around where that car was located. And I know that the cleanup efforts have actually been extended due to official documentation. Could you guys speak to that?
Yes, I spoke about earlier our response actions after the historic flooding event. There was a car that washed into one of our active excavations, and we surveyed the car. We had several pieces of large equipment like excavators and water storage tanks and things that were also submerged with stormwater. We also monitor, we sample stormwater runoff from our active excavations. That's part of our ongoing environmental monitoring program. No spread of contamination. The vehicle was not impacted other than obviously it was totaled by flooding, not by radiological contamination.
Her question is the difference between the source area.
Oh yeah, the area that flooding occurred is across the street, across from McDonald Boulevard. It is a SLAP's vicinity property. So when we say the source sites have been cleaned up, the St. Louis Airport site is a source site, and his future along Laddie Avenue are the 2 source sites.
All right. Does someone want to take the next question before they go up off the chat? It says, by what U.S. state, national, or international expert scientific bodies on ionizing radiation is SEM/EDX or similar methodology recognized or otherwise acknowledged as a method for radiation dosimetry or radiation dose assessment?
I'll do that first if you don't mind, then you can have I'll give you the microphone. So in my discussion that I gave earlier, in my presentation I gave earlier, I referred to Dr. Katolfin's methods. They're very useful in forensics for determining if a particle exists, if a contaminant exists, but there is no organized body that has recognized it for the use in exposure assessment or dosimetry.
Thank you. The US EPA actually has a standard methodology for environmental analysis of SEM EDS. And also we talked about the ICRP dose conversion factors and how these are used to take the data from the SEM process and come upon through a standard method the actual absorbed energy dose from these particles. And we're using standard methodologies and standard setups for this, but it is over and above the work that is done where we look at external doses of radiation from what's actually in the ground. And as we've learned from the asbestos problem and the lead paint problem, one has to look both at what is gross bulk contamination, like we still have at Coldwater Creek, but we also have to look at what's happening from a public health perspective about the dose received from particulate matter, which has a very strong impact on our health.
Okay. If uranium is out of equilibrium, how can U-238 act as a good surrogate for all uranium?
That's a fast answer.
The quick answer is sometimes it doesn't. Remembering that U-238, U-234, U-235 were actually removed by the Mallinckrodt process, that was the point of doing the work. It means that the dross, the waste that's left over, is enriched in thorium-230 and radium-226 compared to that original radium. So in fact, the indicator material of choice is really going to be the thorium or radium. But there are places outside of Coldwater Creek, particularly in those source areas, where the uranium is much more of an actor because we're dealing with wastes that include the original feed materials from Mallinckrodt, not just the post-processing wastes that were put at the two source sites.
Yeah. Oh, I'm sorry.
Sorry, I just like to point out that Mallinckrodt did not enrich uranium. They only processed it into ore. So the original uranium isotope ratios that you would find in the ore would still be present in whatever their uranium that went out as the waste product. The process that Dr. Yeah, so he had put up the chemical processing. You'll have to look at those slides for that.
3 seconds.
Enrichment is the term used when you change the 235 to 238 ratio. No enrichment was done in St. Louis. The reactors that where the uranium was used were actually natural. You ran on natural. Now reactors don't, and so and weapons don't use it. So there's an enrichment process which enriches in 235. None of that was done in St. Louis.
A question from chat. It says CERCLA allows risk to be set 1 per million. Why was 1 per 10,000 chosen?
So CERCLA has a risk range, an acceptable risk range. One of the slides that I showed up there was what we run into just with natural background contaminants, and how just with natural background contaminants, you see a risk that is well above the CERCLA risk range. So trying to achieve something at the very low end of the CERCLA risk range was difficult. And it was not reasonable. And so that's why we selected it. Still within the risk range, CERCLA acceptable risk range, but that's why that was selected.
Okay, Dr. Kaltofen, why do your interpretations differ from everyone else's in the industrial hygiene health physics community? That's kind of a big.
Yes, I understand. First, I'm going to say that question includes a conclusion, but we'll put that aside for a moment and say one of the things that's really important is to actually consider some of the intricacies of who is being exposed and how. And in order to do that, I'm not relying on my own work. I'm relying on the work of the Center for Disease Control, the Agency for Toxic Substances and Disease Registry, the United States Environmental Protection Agency. And these are the agencies that made the statements that there isn't a so-called safe level of ionizing radiation, that in fact Coldwater Creek, when it floods, is depositing radioactively contaminated material that is a significant concern to people who live or work or recreate along Coldwater Creek. So while there may be some differences in how an industrial hygienist, a health physicist, a pediatrician, and an environmental inspector for EPA might look at work, the decision that these materials can exert what's potentially a biological impact of concern on children in schools that are along this waterway ultimately comes from EPA and ATSDR and not from myself.
Marco has talked a few times in his presentation now about ATSDR, which is the Agency for Toxic Disease Substance Registry of the CDC. Actually, when the ATSDR did work here to try to evaluate cancer clusters along Coldwater Creek, they did find that there was elevated cancer, but they determined that there is no way for them to tell if it was from radiation or from the creek. So the kind of study design that they use, which is a cross-sectional study design, which many of the epidemiology students or other public health students know, were the ones that ATSDR used. And as you know, those have a lot of limitations for actually coming to conclusions about whether or not something causes cancer. So in fact, ATSDR has never determined that contaminants in Coldwater Creek have increased cancer due to radioactivity along those neighborhoods that we're talking about.
Next, we are running out of time, so I'm afraid we're not going to get to everyone's questions. Maybe we could post these to the group and have some responses after the fact. Let's see, Dr. Lewis, is it possible for the numbers to be misinterpreted or manipulated to produce fear in a community to achieve an agenda or objective outside of public health, safety, and social justice?
All right, we've got 2 microphones here. That's a really difficult question. Look, I don't question any of the motivations of the people here today, Dr. Katolfin, Sobotka, Dr. Rankin's here and so forth. I don't question any motivations. We all are here to try to protect the community, children. I talked earlier about fear and how fear can become sort of an epidemic. I am concerned that we might cause fear among a community where it's not justified. I don't think it's justified here.
Okay, one for Jonathan. Based on your JANA studies, do any additional schools in the Hazelwood School District require tests for anything other than radon?
We are currently partnering with the Army Geospatial Center to evaluate all of the Hazelwood School District properties. And in conjunction with that, we are doing assessments of the broader North County area, to determine, look at historical photos, historical soil movements along the 100-year floodplain of Coldwater Creek and beyond even. So we are doing more. A lot more is coming to address. There is actually like 32 schools along within the Hazelwood School District that we are going to be looking at, or currently looking at. There are other schools as well on the other side of the creek. So we are looking at all those things. We are assessing those. Again, historical photos, historical development, soil movement, channel improvements of Coldwater Creek. So yes, those things are being done.
All right, Dr. Catalfin, using your argument that one man-made alpha particle is too many and that there could, that they could be tracked to a school, what is your recommended solution? It would seem that cleanup or abandonment of all of St. Louis North County.
First of all, there's no difference between an alpha particle that's fully natural or that's industrial. I think we've talked about this today. They have the same impact regardless of the source. And the issue that we have here is that this is a random statistical event that ultimately, in order to destroy a cell nucleus, it does only take one alpha particle. And we have often talked about how cancer is random. If there is a cancer-causing agent of any kind in a community, you may or may not get it. It may or may not have anything to do with your behavior. It is just that, random. So as we put more alpha-emitting material into a person's environment, the statistical risk of that one alpha particle impacting such a way that it has a biological or a health impact increases. So as different agencies have told us, what we want to do is minimize that as much as possible. And this is not rocket scientists. This is, there are a lot of ways that we can remediate these materials, and money is being well spent to address that. But abandonment from one particle is not what we're talking about. We're talking about testing and remediating to reduce the risk of exposure to alpha radiation that has a health impact as much as possible.
All right, I have a question in response to that. One grape could cause someone to choke. Should we stop all of the grape production in the world because that would minimize the risk, especially with grapes?
We're not talking about grape. We're talking about radioactive.
I'm just asking because it's the same claim, because if something can cause risk, shouldn't we have to look at the overall risk and likelihood of the situation in order to establish what to do instead of the risk of one event might cause it, therefore we must stop it entirely? Because I agree that radiation is a serious problem.
But you're choosing to eat a grape, right? You're choosing to not cut it up for your child, whereas you don't get the choice to choose where your kid gets to go to school.
Yeah, now these are all very good points. And, I think it's, but I mean, levels of risk. What's everyone, comfortable with accepting? But there's some risk that we take because we choose it, and there's some because it's placed upon us. And that's, yeah.
Clarify, just have a clarification point that there's a difference.
I'm happy to address even a non-serious question. As a parent and as someone who has raised toddlers, no, you don't give them a grape to eat when they're too young to eat it responsibly. And no, you don't have to remove all of the grapes from the planet, but you don't give them to 6-month-olds. I mean, this is fairly simple. And engineering works that way too. We don't need to get all of the radioactive materials to zero because we understand that's more than we can afford to do. But we do know we should be prioritizing alpha-emitting isotopes, particularly those related to the Manhattan Project work done in this area. And we very especially want to do that when talking about younger people, because the benefits of that are very significant, especially if you are that St. Louis family.
Anyone want to follow up on that?
I just want to add, one thing about alpha particle. We keep talking, everybody gets hung up on this one. I've had this question many times at our community meetings and things. Radon is an alpha emitter. We are all breathing in alpha particles right now. Okay, you breathe them in every breath you take. So to say things like no radiation is acceptable or no amount of radiation is acceptable, that's a little bit misleading. I know the EPA may say something like that. I'm just without trying to, provoke fear in everybody that's going to ask me about radon exposure for the rest of my career. You have to put things in perspective. There are alpha particles all around you. Okay. We are removing contamination in North County, including Jana, adjacent in Corner Creek, has thorium-230 contamination that is an alpha emitter. We are reducing those risk factors for future users of that property.
All right, I wish we could go on and on, but we do have a hard stop. Thank you all for coming today and staying through several hours of presentations. If you could be